All right, welcome back. This next part of R7 focuses on simplifying radicals. All right, so about simplifying radicals, I think one of the things that makes a challenge to simplifying radicals is that how do you know when it's completely simplified? Sometimes you think it might be simplified all the way, but you're not entirely sure. So here's a list of things that you can look for, and then you'll know why it's not completely simplified. So the radicand has no factor raised to a power greater than the index. The index, guys, is what the root number, right? So here we have the square root, so the index would be 2, okay? The radicand has no fractions. We can't have any fractions in. Oh, and the radicand, guys, the radicand is just what's inside the radical. Just to remind you of that, if you forgot that from like 3rd grade when you first learned about it. But the radicand is like what's in the radical. The index is the root number. So the radicand can have no fractions in it. The denominator cannot contain a radical. We have to rationalize that denominator. Exponents in the radicand and the index contain no common factor. I mean, I'll kind of show you what that means. All indicated operations have been performed. Okay, that's what we're looking for. And if all those conditions have been met, then the radical is simplified. All right, so we're gonna start off with a pretty easy one here. The square root of 175. I'm gonna start by breaking it down. You can choose any way you wanna factor it. Ultimately, you'll end up with the same factors, but I wanna choose, how about 25 and 7? Okay, so let's analyze this and let's look and see why it's not simplified. It says, the radicand has no factor raised to a power greater than the index. Okay, well that doesn't really apply. The radicand has no fractions, that doesn't really apply. The denominator contains a radical, that doesn't really apply. The exponents in the radicand and the index contain no common factors. So that's the one that's a problem here. Because another way to write 25 is 5 squared, right? So if we have 5 squared and this root number or index is 2, it's not simplified. So, I mean, this is pretty basic. I already think you knew that, but this is just the rule as to what you can really look for. So if we were to break 25 down to 5 times 5, this is the prime factorization. 5 times 5 times 7 is 175, but when written like this with this factor tree, I think it's easy to see the pair. Pairs get to go outside, low numbers have to stay in. If they don't have a pair, they stay in. If you have multiple groups of pairs, you multiply the pairs together. If you have multiple solo numbers, you multiply those together. So here I have a 5 going to the outside, and then I have the square root of 7 left over. And that would be it. Okay? That would be it. Wait, we went from even to odd. Is absolute value required? I don't think so, because it's not a variable. We already know 5 is positive. Okay. All right. Let's say we take a look at another one. Let's do the negative 3 times the 5th root of 32. Negative 3 times the 5th root of 32. All right, so the reason that this one is not simplified is because 32 can be broken down. And we're gonna have a number that's gonna be able to come out with that negative 3 that's already out there. So if I was to break it down, I could do 4 and 8, 2 and 2, 2 and 4, 2 and 2. Oh, this is a happy problem. Everything got to come out because we have 5 different 2's. So I can pull out a 2 with a negative 3 that's already out there. So that's just gonna be negative 6. And there's nothing left on the inside, okay? It's a good one, I like it. Negative 2. All right, let's do one more. Oh my. This last example, they didn't pull any punches. Let's see, I have the cubed root of 81 x to the 5th y to the 7th and z to the 6th. Okay? So, let's start by breaking this 81 down. I'll break that down to 9 and 9, 3 and 3, 3 and 3. So I have a triplet of 3s that get to go out. So we're gonna pull out a 3, but this guy's gonna have to stay. We're gonna have 1 3 left over. So the 3 on the outside. Do I have enough x's to bring an x out? I have 5 of them being multiplied right here. So since there's 5 x's being multiplied, I can pull out 3 of those 5. My 1 trio of x coming outside, and 2 left over, so we'll deal with those in a second. Do I have any y's that can come out? Yeah, I do. I have 7 y's being multiplied together. And every time I have a trio of y's, I'll pull a y out. And I'll have 2 trios. That would make 6 of the 7 y's. So out I have coming y squared. I'll have 1 left over y. We'll take care of that in just a second. And then z to the 6 is going to give me 2 trios of z's. So that means z squared will come out. And then I have left a cubed root. We have the 1 left over 3. I have also, I had 2 x's left over because I pulled out 3 of the 5, which left me 2. So I have x squared. And then I have 1 y left over because I pulled out 6 of the 7 y's, with leaving me 1 y left over. And then I think every z went out because I had 2 trios of z's. That accounts for all 6 of them. So I have no z's left over. This is it. Now, do I need any absolute values around any of those variables? I don't. The reason is we started with an odd root, okay? Odd roots can have an outcome that's negative, so it's no big deal. Even roots can have an outcome that's only positive, so we don't have to worry about the absolute value rule this time. All right. Thank you very much. More R7 coming up.